Hello everyone. In this video, we are going to use Jamovi in order to help us create confidence intervals of means. Let's take a look at our scenario real quick. It says, oftentimes we do not know the population mean and standard deviation, but that is many times exactly what we are looking to approximate. This is why we do studies and polls to discover what we do not know. We can use confidence intervals and bounds to help us make an approximation. All right, here it is. O'Shea is out trying to do a study on the number of hours students at his college spend on their phone each week. He randomly selected 83 students and had them report their numbers of hours on their phone for a week. Data recorded here at the bottom. He decides a good place to start is trying to determine the average number of hours spent on their phone each week. He wants to have a 91.75% confidence level. Okay, so let's go ahead and let's look at the data. And we have this hours on phone per week. We're just going to go ahead and highlight it. We're going to copy it. We're going to bring it over to Jamovi. Let's paste it in. Now, if you notice I made a mistake, I accidentally put this hours in here. If you do that, you can just click on this one, do a right click, and you can say delete the row. It'll say, do you really want to delete it? I'll say yes. And then we need to do a little bit of editing to get this in the right frame or in the right data type. So I'm going to label this as hours. And we know that this is going to be continuous and decimal. And so we've got our data imported incorrectly in Jamovi. Okay, so let's go ahead and let's look at this first question. So here we are trying to take our scenario and break out some basic vocab so we really understand what's going on. So we have like parameters, statistic, population. We need to get these things in correlated with the right definition. So the first thing that we will look at, we'll just try to grab the parameter. Now remember, the parameter is some truth about the entire population. So if we look right here, it says the mean number of hours spent on the phone for the entire college. That's what we're looking for our parameter. So we'll just go put an A there. Now that we have the parameter, let's jump down and do statistic, because the statistic is the truth about the sample. So this would be the mean number of hours on the phone by the 83 students selected. So we'll put that as C as our statistic. Let's go look at our population now. So the population is all of the students at O'Shea's college. So that's going to be our D real quick. Then if we look at our sample, that's just going to be what is that subset? That'd be the 83 students selected to measure the number of hours spent on their phone for a week. So that's going to be E. All right, we just got left is the data and the variable. So the data is just the list of the recorded hours on the phone each week. Okay, so we can put that as the data. So that's B. And then the left is the number of hours spent on the phone by a single student. That's like the question that's being asked, how many hours do you spend? That's our variable, and we can put that as F. All right, so very important to know how to track those down. I would highly suggest you start off with the easiest ones, the ones that you know the best, so that you can kind of eliminate all of the easy ones and you're just left with some ones left over. And it's oftentimes easier to figure them out at that point. Okay, so this next question says, does O'Shea need to worry about the distribution of the individual's time spent on the phone? Okay, so this is kind of our central limit theorem question. It's like, do we need to worry about the original distribution? Now, the central limit theorem was so helpful because it says that we don't need to actually worry about the original distribution. We don't need to know anything about the distribution of the individuals as long as our sample is big enough, because it means that the sampling distribution, or the distribution of the means that we were to grab repeatedly, is normally distributed. So because our sample is sufficiently large, then we don't need to worry about it. So no, we don't need to worry because the sample size is sufficiently large to invoke the central limit theorem. So we can click that right there. Now the best point estimate of the average time on the phone. So basically this is saying, hey, what do we think the average number of hours that this college per student, spends on their phone? Now, the best estimate that we have is the sample mean. So we can grab that real quick. Let's just go into our exploration. Let's go to our descriptives. And when we have our descriptives pulled up, what we're going to do is we're going to bring our hours over to our variables. And instead of doing variables across column, we can do that. You can also do it across the rows. I'm going to leave it at the column just because it helps with space management. I'll go down to the statistics. I really don't need how many are missing. We can keep the mean and the median if we want. I'm actually going to take out the median. I want to take out the minimum and the maximum. But I am going to leave in the standard deviation, and I actually want to put in the standard error of the mean as well. Okay, and then I want to look at these results. The results that I have is that I have 83 samples, have this mean of 16.93798. And I've got my standard error, my standard deviation. Okay, so real quick, let's remind ourselves what the standard error is. So the standard error is like is a measure of spread. Basically, it's a measure of how far away from the mean we are. So, and then the standard error, let's put this in a comment real quick. Remember, the standard error is just equal to the standard deviation divided by the square root of n. This is going to be handy for us in some of our equations coming up. So the standard error, we actually have it right here. It gives it to us with the standard error of the mean. It's the standard deviation of 3.0 level. Just do it. We can say that the standard error equal to 3.0, we'll just do 69 divided by square root 83. We can just type in SE. Let's run this really quickly. And we see that this gives us 0.3369, and we got 0.336. I believe that's a 9 over there. Yep, 3369 as our standard error. So the nice thing is you actually don't need to do this calculation. You just need to tell Jamovi to give it to you in the descriptives. Okay, so scroll on down, and we can say that the best point estimate of average time on the phone is just going to be this 16.937, roll over and grab it, 9379. Okay, let's give ourselves a little bit extra room. Okay, so the next part that we are being asked about is a confidence interval. So we're looking for a confidence interval for the average phone time between two times. So when we're looking for these between, we're looking for, it's actually a two-tailed confidence interval. We're looking for the upper end, we're looking for the lower. So real quick, I am going to give us our equation that we are going to use. So we're going to copy this, and I'm going to just paste it into our editor. And for a two-tailed confidence interval, this is the equation that we are working with. So the confidence interval equals x bar plus or minus this t critical times the standard deviation divided by the square root of n. And this standard deviation divided by the square root of n, we can just replace that with the standard error, because it equals the same thing. So we know what x bar is. That's our sample mean that we just calculated. We know what the standard error is because we calculated it, and also Jamovi just can give it to us. So the last thing that we need is this t critical. So let's actually use a graphic real quick to kind of help us understand what exactly is going on. The only other thing that we need to know is our alpha real quick. So our alpha that we need is, remember, 1 minus the confidence level. So we can say that, say alpha equals 1 minus 0.9175, and I can type out alpha. And if I highlight this and run it, it will give me that my alpha is 0.0825. I'm going to need that in just a second. Oh, the other thing that we can do to help us out is if we click on this little gear box, we can say that it'll show the code as well, and it kind of helps us keep track of what's going on. Okay, so now that we've done that, let's actually go and calculate out our confidence interval. So we want this plus or minus value. Here's what we can do. Let's go first and look at distraction. Let's grab our t-distribution. Now, when we do our confidence intervals, we have a couple of options. We have a whole bunch of options with using the z-distribution, and we have a whole bunch of options using the t-distribution. Remember, the z-distribution is really, it's just the normal distribution, and the t. And so when we're doing confidence intervals, we have to know, what are we talking about? Are we doing a normal distribution? Or are we doing a t-distribution? And the key comes down to, what type of standard deviation do we know? Do we know the population standard deviation, or do we know the sample standard deviation? Now, if we were to know the population standard deviation, that would have to be given to us in our scenario. We would have to actually know this population standard deviation before we even did the study. And in this case, it doesn't give us that information. So the standard deviation that we're actually using, the standard error that we're actually using, is coming from the sample. And if it's coming from the sample, then we should be using our t-distribution. Let's go ahead and click on our t-distribution. So when our t-distribution comes up, it's going to give us a graphic and it's going to give us a bunch of options here. It gives us some parameters that we need to put in, and then we need to actually compute a quantile in order to get this t-critical. Real quick, let's go back to our editor. So in here, we need to know what are our degrees of freedom. And the degrees of freedom is just the sample size minus 1. So our sample size is 83 minus 1. And if we just type degrees of freedom here and we run this, it's going to give us as 82. So we know that our degrees of freedom are 82. I'm going to go back and click on my t-distribution. Degrees of freedom, 82. All right, this is a Greek symbol lambda. We're just going to leave it at 0. It is a kind of more advanced thing that we can play around with. We're just going to leave it always at 0. So the next thing that we need to do when we go and we look at our equation up here is we know x bar, we know this standard deviation, we need to figure out this t-critical. Now, right below it, I put in what we need to know in order to run this t-critical. And the t-critical, we need to know the degrees of freedom, and we actually need to know alpha divided by 2. Let me show you why. This graphic does a really good job. So when we are doing a two-tailed confidence interval, basically we're going to pretend that the mean is right here at our t equals 0. So we're going to put our mean right there. And then we're going to go plus and minus some number of standard deviations above and below the mean in order to grab the range where we think that the true mean is. Because we actually don't know what the true mean is of our population. We know what this mean of the sample is, but we know that that mean isn't exactly true. Maybe we got enough results that made our sample mean a little bit too high, or maybe the results that we got made our sample mean a little bit too low from what the actual mean is. So what we're going to do with this confidence interval is give a range, or we're going to give a net of where we think that this true mean is actually located. So in order to do that, we need to know how many standard deviations above or below do we actually want to go. And that is where this critical t is actually going to tell us what to do. So I'm going to say compute these quantiles real quick. And this p is going to give us this range, this middle range of where we think that this quantile is going to be. So I am going to put in here 91.25. Is that right? Hold on. Let's go back here. 91.75, excuse me. 91.75. And since I'm doing this central interval quantiles, let me enter. It says we're going to go this far above and below, and this is where we're going to make our confidence interval catch. We think that the true mean is actually located plus or minus 1.758 standard deviations from the mean. Okay, we need this number right here, this 1.758. Let's go back up here. And what we're going to do is we're actually going to give our confidence interval upper. So confidence interval upper equals, let's start off with our x bar. Our x bar is this 16.93798. And then we'll do plus. And we need this t critical that we just saw, 1.758. 0.758 multiplied by the standard error that we got from up here. Our standard error is 0.33690. Then we can get that confidence interval upper. And let's just run this thing again. We have 17.53 as our confidence interval. All right, one thing that we might want to do here is the RJ editor, it only is going to give out to 2 decimal places, but we can fix that. There's a little piece of code that I don't expect anybody to have known before this point. But if you just type in options digits equals, and we're just going to put in a 7 here, it's going to give us some extra decimal places. Let's just go ahead and run this whole thing again. Run that, and now it's given us out to 17.53025. That's great. That gives us our confidence interval upper. Now, our confidence interval lower is the exact same equation, except for one difference. Instead of doing a plus, we are going to do a minus. And now we can hit enter. Or let's highlight it all and let's run it again. So now we have the upper and the lower right there. So let's go ahead and come on in. And now we can put in our lower here as 16.345. And we can put in the upper as 17.53025. And I pulled those from our confidence interval upper and our confidence interval lower. Okay, so now we need to select an appropriate conclusion about the confidence interval. All right, so some of these are poorly written and some of these are well written. So let's go over like each of them and say kind of why they're good or why they're bad. So let's start at the top one. There's a 91.75% chance that the sample mean spent on the phone is between these 2 hours. Okay, so the problem here is that, well, two things. One, we're giving a probability to the sample mean. And we know what the sample mean is. I'm 100% sure what the sample mean is. It's right here. I calculated it. So that one's bad. Let's go down here and look at the next one. There's a 91.75% chance that the true mean time is spent on the phone for O'Shea's College is somewhere between these 2 times. Okay, the problem there is that we're giving a probability to something that is actually fixed. We think that the true mean time that students are spending on the phone is a fixed value, and that we're casting a net to try to capture the true mean. The true mean isn't moving. It's kind of a technical thing, but it's really important. So this is a poor one too. This third one is actually what we're looking for. We are 91.75% confident that the true mean time on the phone is in between these two. This is the method that we're going to use to correctly talk about this. We are confident that the true mean has been captured by our net. And then the problem with this one is that we're confident that the net has captured the sample mean. And that one's wrong because when you're doing a two-tailed interval, that the sample mean is in the middle of that interval. So anyhow, that one's wrong as well. Okay, so now what we're asked to do is suppose that O'Shea wanted a confidence interval to claim that the average phone time was at least some value. All right, so if you wanted to say at least or at most some value, what we are doing is a one-tailed confidence interval. So what we're going to do here is O'Shea wants a confidence interval to claim that the average time was at least some value. So from some value all the way to infinity. And that's how you do infinities here in MyOpenMath is just 2 lowercase o's. Okay, so this is one-tailed and we need to figure out what is this lower bound. Okay, and then we can do a interpretation, and then it looks like we want to do a one-tailed going the other direction and an interpretation there. So we're almost there. Let's go back here. And what we actually need to do is we need a new confidence interval equation. So in this one, let's copy this and let's paste it in. This is a one-tailed confidence interval equation, and it is almost identical where it's still x bar, and we could either do plus or minus this t critical times the standard error. And the t critical is a little bit different. Instead of using alpha divided by 2, we're using just alpha here. And that's because we're putting all of our error or possibility to be wrong into a single tail. Let's go up and look at this graphic again. So when we did it previously, when we were doing a two-tailed confidence interval, we put our possibility to be wrong into 2 tails. What we could also do is if we click on this cumulative quantile, we can toss all of our error into a single tail, either above or below. And I'll show you how to do that in just a second, how we can flip the side of where the tail is. Okay, so let's take a look again at exactly what we're looking for. We're looking for an at least some value. So we actually need to find a lower bound for right now. So for finding this lower bound, we need to get this a minus sign. And now we need this new t critical. Let's go back and look at what we were working with before. And we're actually going to need this alpha value, this 0.0825. Remember that. So we need this 0.0825 because when it says the cumulative quantile, it's putting all of that 91% into this side and our error in this side. So we have 8% roughly of error on this side. If we want to flip it to the other side, we can do 0.825 and hit enter, and it just flips it to the other side. Now, if you notice real quick, look at what happens to the quantile. All that happens is we're saying when we want to put that 8% that is going to be our error rate, we can flip it to one side, or if we put it back to the other, let's put 91.75. Pay attention to the quantiles right here. When I hit enter, the only thing that changed was the positive or the negative sign. So that's actually really handy for us. We're going to put in this 1.401 right here. 401. Oopsies. Nope, not there. We need to calculate that. We need to go back to our calculating out our confidence interval. So here I am going to copy this, paste it, and then we need to change out this t critical to 1.401 because instead of putting our error to one side, we're putting it to two sides. And just put this back to 0.825. We have this negative sign because we're to the left. We're making it from a specific value and everything above. Go back up here to our calculation. And we have our mean minus this t critical times the standard error. And here, if we do the confidence interval lower again, we rerun this guy, it's going to give us 16.45 or 46, sorry. 16.46 will do 598. And then when we come down here and we look at, we can look through these again. The reasoning is the same as above, but we're looking basically for this. We are 91% confident that the true mean time spent on the phone is at least this 16.47 hours. Okay, coming on down. Now we want to do it the other direction, whereas O'Shea wanted a confidence interval to claim that the average phone time was no more than some value. So this one we're going to go from negative infinity, and we are going to go to some upper value. So if we go back and we look at our distribution here, the only thing that's going to change is now we're going to go from 91.75. We flip this to the other side. No more this value or less. And it's still, this t critical is still 1.401. Going back to our little calculator in here, we can then say that the lower one, sorry, this is the upper critical value when we're doing a one tail. So we'll do one tail lower bound. For this next one, copy all of that, paste it, one tail upper bound. Everything is identical except for this plus sign right there. So we'll change that from negative to a plus. And let's go ahead and run that. Now we get 17.40998. Let's put it in 17.40998. This is still a one-tailed confidence interval. And we can say that we are 91.75% confident that the true mean time spent on the phone for students at O'Shea's College is no more than 17.41 hours. Okay, so that is how you go through and you actually go through and grab the values and calculate out these, if we wanted to do a two-tailed confidence interval or a one-tailed upper bound or a one-tailed lower bound confidence interval. Okay, now there is a shortcut in Jamovi that we can use. Very useful, but in order to do one-tailed, we have to be very, very thoughtful about what we're doing. So I wanted to show you how you can do it with calculations and also how you can do it using. So in Jamovi, what you can do is you can click on this ESCI. So if you haven't installed it, you can go to the modules and install the one that gives you the ESCI options. We're going to click on ESCI. And we're going to estimate our mean. Click. Okay, when we are clicking on this one, what it can do is we can actually just go and tell it to take the hours that we have, put it into our measurement, give us a 95% confidence interval, and if we go look at our values up here, it's going to give us our upper or lower. Now, it doesn't match what we have because we didn't do a 95% confidence interval. We did a 91.75% confidence interval. Once we do that, it gives us essentially the same numbers. There's some slight rounding errors because of we used when we calculated out our T critical, we did a calculation with a rounded number. So these numbers are actually better, but to about 3 decimal places, they are rock solid. Okay, so that's how you can do a two-tail, and the nice thing, it also gives it like a histogram of the sampling distribution. It also shows like, this is a nice plot that shows the sampling distribution and how much narrower the sampling distribution is. It's a pretty cool little thing that this does. Now, the one thing that it doesn't do is it doesn't allow you to do a one-tailed confidence interval. But there is a trick that you can do in order to get around that. Here's what you can do to get around it. So what we need to do is we need to go back to our Jamovi stuff here. And what we need to do is we need to actually figure out a little trick. So we have alpha here, and we actually need to know what alpha times 2 is. And we need to do, let's just do alpha times 2. Alpha times 2, I'm just going to label this as, we'll just label it as called A2. And then we need this new confidence interval. So we'll do like CI new equals 1 minus alpha times 2. And let's just do this CI underscore N so we can see it. And we'll see A2 as well. Let's just run this real quick. Okay, so we have our original alpha, which is 0.825. Our new alpha, or alpha times 2, is this 0.165. It's just taking alpha times 2. And our confidence interval new is going to be 0.835. Okay, remember this 0.835. It's going to be helpful for us. So we're going to take that 0.835 and we're actually going to go back into our estimates here so that we can get our confidence interval. So we're going to do 83.5. Double check, make sure that was right. 83.5. I'm going to hit enter real quick. And should we do a histogram? No, we'll go back to the dot plot. Okay. So when I have made my confidence interval at 83.5, I want to show you what I have actually done. So what I've actually done is it's giving me this upper and this lower value. Now notice, if you look at these upper and this lower, and we go back to our one-tailed confidence intervals, the lower is this 16.465, excellent, and the upper 17.4099, 17.4099. So we nailed it, but it gave it to us as both as the upper and the lower. Let me show you graphically what this has done. So when we have doubled our confidence interval, when we did it as a two-tailed in that example, we basically told it to calculate both this interval right here and the lower interval at the same time, which is kind of like what you do with a two-tailed. So we just kind of leveraged how Jamovi is calculating this upper and this lower with a two-tailed kind of hack in order to make the two-tailed confidence interval give you both the one-tailed upper and lower values at the same time. So anyhow, if that is just blowing your mind, that's fine. You can always go back and we can use the calculations that we did, and they work just fine. But if you understand kind of this process that we went through in order to get the upper and the lower for the one-tailed, confidence intervals, you can use this trick as well. Anyhow, I hope that that helps you out and that you have great success in calculating confidence intervals for the means on your own assignments.